Okay, let's jump right in. We're going to walk through how to pick the perfect statistical tool for your research from start to finish.
So here it is, the big question every single researcher has to ask. Is what I'm seeing a real effect, or could it just be random chance?
And that's exactly where inferential statistics come into play. They're basically the set of tools that help us answer that core question. Is this a real difference, or is it just a fluke? So let's start with a really common scenario in research. You want to see if there's a meaningful difference between the averages of a couple of groups. Okay, so if you're just comparing two groups, the t-test is absolutely your best friend. This table lays it all out. If you've got two totally separate groups, say a class using an AI tool versus a traditional one, that's a job for an independent samples t-test. But what if you're measuring the same group twice, maybe a pre-test and a post-test, to see if their scores improved? Well, that's a paired samples t-test. And finally, if you just want to see how your group stacks up against a known number, like the national average, you'd use a one-sample t-test. See, each one has a very specific job. Now you might be thinking, well, if I have 3 groups, I'll just run a bunch of t-tests. But hold on. Here's the catch. Every test you run has a small chance of being wrong, of giving you a false positive. And those little errors can add up really fast and lead you to a big wrong conclusion. That's why we need a different tool for this job. And that tool is ANOVA, which stands for Analysis of Variance. It lets you compare the averages of 3 or more groups all at once without that risk of piling up errors. A one-way ANOVA is pretty straightforward. You're looking at one factor, like comparing scores from 3 different writing tools. A two-way ANOVA gets a bit fancier, letting you look at 2 factors at the same time. And if you're tracking the same group over 3 or more points in time, that's when you'd use a repeated measures ANOVA. But here's something you absolutely cannot forget. These powerful tests, they have rules. We call them assumptions. And you have to check them if you want your results to be valid. Think of it like a pre-flight checklist. You've got to check for normality. Is your data shaped like a bell curve? And homogeneity of variances. Do your groups have a similar spread? And then, if your ANOVA comes back and says, hey, there's a difference somewhere in here, that's when you bring in the post-hoc tests. They're what help you pinpoint exactly which groups are different from each other. Okay, we've covered comparing groups. Let's switch gears a bit. What if you're not looking for differences, but for relationships? How 2 variables move together. That's where correlation analysis comes in. It's a way to measure both the strength and the direction of a relationship between 2 things. For example, does higher motivation tend to go along with better grades? Correlation gives us a specific number to answer that. And if you remember one thing from this whole section, make it this. Correlation is not causation. Just because 2 things are related doesn't mean one causes the other. It's the oldest rule in the book for a reason. So if your data looks pretty standard, continuous variables like test scores or GPA, and it's normally distributed, your go-to is going to be Pearson's R. It's probably the most common correlation test you'll ever see. But what if your data is a little different? Maybe you're working with survey data that uses a ranked scale, like strongly agree to strongly disagree. That's not continuous data. For that, or for any data that just doesn't follow a bell curve, Spearman's correlation is the right tool for the job. And finally, there's Kendall's tau. This one's your best bet when you have a small sample size, or if your data has a lot of tied ranks, like if multiple people get the exact same score. It's a bit more conservative, which is a good thing when your data is a little messy. Okay, so knowing 2 things are related is great, but what if you want to take it a step further? What if you want to use one variable to actually predict another? Well, that's where we move from correlation to regression. So here's the key difference to lock in your brain. Correlation just tells you that 2 things are moving together, but regression goes further. It actually creates a model to predict the value of one variable based on the other. Correlation is about association. Regression is all about prediction. And this breaks down the engine of regression perfectly. You have your predictor, X, which is what you know. You have your outcome, Y, which is what you're trying to predict. The residual, that's just the error, the gap between your prediction and what actually happened. And the real star of the show is R squared. It's a number that tells you how much of the change in your outcome is explained by your predictor. A higher R squared means a better model. Simple as that. What regression gives you is the mathematical formula, just like this one, that best fits your data. You can then plug in a number for X, like a student's motivation score, and the equation will spit out a predicted GPA. It's pretty powerful stuff. All right, you did it. You ran your test, and now you're looking at the output.
Let's break down the two most important numbers you need to understand to make sense of it all. Now, this is a spot where a lot of people get tripped up. You've got two numbers, the p-value and the effect size. The p-value answers a simple question. Is there an effect? If it's low, it suggests what you're seeing probably isn't just random luck. But the effect size answers the other crucial question. How much does it matter? It tells you how big and important that effect is in the real world.
And you absolutely need both to tell the whole story. It's possible to have a result that's statistically significant, but the effect is so tiny it's practically meaningless. As this example shows, a good interpretation reports both. So you can say not just that there was a difference, but that it was a large difference that had a real impact. Seriously, burn this into your memory. The p-value tells you if it's real. The effect size tells you if it's important. You need both to make your research truly meaningful. And that's really the ultimate question you should take with you. So you ran the numbers and your result is significant. Great. But is it meaningful? Is the effect you found big enough to actually change how we teach or learn or understand the world around us? That's the real story your statistics should be telling.